What is the maximum number of reduced moves that can be taken by a bottom-up parser for a grammar with no epsilon and unit production to parse a string with n tokens? Now, epsilon productions are of the form A gives epsilon and unit productions are of the form. Wait a minute. This is not how a unit production looks like. Unit productions are always of the form capital A gives capital B, that is a non-terminal or a variable giving another non-terminal or variable, but never of the form A gives small a, where capital A and small a are variable and terminal respectively. The source of this definition is given in the description below. IIT Bombay got lucky while setting up this paper because you could get the right answer by just selecting a grammar without A gives epsilon and this production, which is actually not a unit production. And hence there was no need of giving marks to all for every student for this question. However, I will show you the right question and the right answer associated with that question. What is the maximum number of reduced moves, blah 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 blah, with a grammar with no epsilon, that is of this production, and no unit production, that is A gives capital B, and with no production of the type A gives small a. All three are required. I will give you the reasons for why we require both no unit production and no production of the type A gives A in the end. For now, let us see how to solve this question. Let us take the example of a shift reduce parser, which is actually a bottom-up parser, to better understand how a bottom-up parser works to parse a string with n tokens. Let us take the example of this grammar given below. As you can see, it has no epsilon productions, unit, or productions of the type capital A gives small a, and hence is a perfect example. We will try to parse a string with n tokens. In our case, we are parsing the string triple A, and hence n is equal to 3. As you can see here in the input. Also, shift reduce parser has a stack and the action. Now what a shift and reduce is all about will be clear once this example is done. So let us begin with this example. Now we have the input A. We will push each one at a time on the stack. Hence this action is called as shift A, and hence A will be pushed on the stack and two A's remain over here. This shifting process actually creates a node small a in the parse tree. So here I'll start drawing the parse tree. Next, again we shift until when? Let's see. So now I have 2a shifted. Now we keep shifting until we find a handle. A handle is nothing on the right hand side of the production which can be replaced by the LHS of the production, and that is called a reduce move. Hence I reduce using S gives AA, and hence now AA can be replaced by S. So capital S is here and we have an input A left. Now again S cannot be reduced further, and hence A must be shifted or pushed on the stack. Hence we shift A, now SA, and now the input is empty, and we have SA. Can it be replaced by something? Yes, it's on the right hand side, can be replaced by on the left hand side, and hence SA is also an handle. So SA can be replaced by S, and here we reduce using the production S gives capital A. Now as you can see, when I shift A, another A is shifted here. Here when I use reduce AA is reduced to S and A. Shift A will shift another A, and reduce S gives SA will give me this tree. Sorry for the wrong diagram, sorry, not wrong, I mean the ugly diagram again, but this is how a shift reduce parser works. And when the answer, I mean when on the stack the root node is left, hence it will be accepted. As you can see, how many reduce moves were required? 1 and 2. Hence for length n equal to 3, there were 2 reduce moves required. Another simpler method of finding the number of reduce moves is just by using the leftmost derivation method. That is, you start off with the root node So S gives SA. Now S can again be replaced by AA, and with this we derive it in two steps, and hence 2 is the number of reduced moves. This is much more simpler than drawing the entire table and the parse tree. Also, since the tree is being formed from bottom to top, it is also known as a bottom-up parser. Now, we know that for n is equal to 3, we get the number of reduced moves as n minus 1, that is equal to 2, and hence B is the answer. But again, I know there is a lot of ambiguity of why A, C, and D are not the answers. So let us look at another example. Now, the mistakes that students make is selecting this grammar. As you can see, to derive or parse a string of length n equal to 4, you require two reduced moves, that is nothing but n by 2, which is not the maximum number of reduced moves. In our earlier case, it was n minus 1, and hence A is not the answer. Now, why shouldn't we use these two productions in our example while solving this question? Let us start off with A gives small a. Here in this example, you can see that to parse a string of n equal to 3 symbols, you have to actually have 3 reduced moves, which is actually of the order n. Since n is not the option, we should not have included this in our example. With this, we learn an important property that to parse a string of n symbols, you can have a maximum reduced moves of n and not more than that unless you have a unit production. Let us look at an example to clarify this. As you can see in this example, to parse a string of length n is equal to 1, you have 4 reduced moves required. As you can see, unit productions are useless and they simply unnecessarily increase the compile time of any program. Again, even though it is greater, there is no relation such as 2n or 2n minus 1, and hence we can never identify, we can never come to know what is the proper approximate answer, and hence C and D also cannot be right, and hence B is the only correct answer. If you like the video, do subscribe and support us. Thank you.